Hey, what's up, guys? This is Chung here. So this time, LeetCode 1898, maximum number of removable characters. I'm gonna upvote this one. Okay, so you're given like two strings s and p, right? Where p is a subsequence of s, and you're also given like a distinct zero-index integer array removable, containing a subset of indices of s. And your task is to choose an integer k, right, such that after removing the first k indices, right, from this removable, from this s, after removing those, p is still like a subset of s, right? So, and you need to return the maximum k you can choose, such that after removing the first k's indices from this from this removable, and then p is still a subsequence of s, right? So for example, we have this ABC, ACB. So the P is AB, and the removable indices is like this, right? The third index 3, 1, and 0. So in this case, we can remove the first two indices, because as you guys can see, after removing the first index, the third one and the first one, it's still like a superset of P, right? But if we remove the second one, sorry, but if we keep removing the first one, then basically this A B C A C B. So if we remove the third one and the second one, third one is this one, right? 0, 1, 2, 3. This one is gone, and the first one, the index 1 is gone. Right? As you guys can see, this one ACCB is still like superset of AB. But if we keep removing, if we removing A in this case, now CCB is not a superset of AB. That's why the answer is 2, right? So that's basically the idea, And there are some like other examples. So the constraints are like 10 to the power of 5, right? I mean, this problem, I spend a lot of time trying to figure out like an optimal, like a better solution, because I think all of you knows that given like s and p, we can check if p is a subset of s in O of n time, right? So basically we use like a two-pointer technique, right? So we have this kind of s here, and then we have another p here. Basically we have a p1 pointing to here, and then we have p2 pointing to this p, right? So whenever basically the p1 keeps moving forward, and whenever we see a matching character with the p2 basically moving forward by 1, right? So by the end, p1 reached the end, we check if p2 also reached the end. If it is, then it's a subset, otherwise it's false, right? And this is the O of n time complexity, right? So, but given the constraints is 10 to the power of 5, if we check the removables one by one, basically we check if we remove the first one, right? After removing the first one, it's gonna take like O of n time. If we check the first two, it's gonna take another O of n, right? So, and then so on and so forth. Basically, if we do it in that way, it's gonna be a O of n squared time complexity, right? So that's why I spent a lot of time trying to find like a pattern to see if there's like a O of n time complexity, where if we can find a way of maybe smartly or more efficiently to detect this kind of the position here, right? But it turned out I couldn't find a better way of doing it. So in the end, it turned out, it's a binary search problem, Surprise, huh? Because, you know, basically, so what is the what is this increasing or decreasing trend here, right? So basically, the more you remove, the more unlikely the P will be a subset of S, right? Because since we're always removing from the first one until some low position, right? Basically, the more basically the bigger the K is, bigger the K is, uh, the the subset, the chance of subset is smaller, right? So basically, by the time K is increasing, and the chance of subset is decreasing. So there has to be a like intersection here, right? Where this is the biggest K, right? Basically, after this one, if K keep increasing like to K plus one, and then the subset, basically this check function, right? P will not be a subset of S. So in the end, there's no fancy algorithm here, like if we can find like a better algorithm, but maybe can efficiently or smartly somehow use this kind of thing to skip something in S, but at least for me, it didn't work out for me. That's why, in the end, we have to go back to like a more basic improvement, which is a binary search, right? Like I said, since we have this kind of increasing and decreasing trend here, it's a candidate of binary search, right? Where the basically we binary search this K here, right? And then we're gonna have like a helper function, right? So the helper function, we have a middle point here, right? And since we're getting this, we're searching the maximum, right? So I think I have already talked about a few binary search problem. Since we're getting the maximum, it means that L will be equals to middle when when this helper function is true, right? Otherwise, it's gonna be the right equals to middle minus one, right? And the helper functions is just the given the middle, which means that we're going to remove the first from 0 to middle index. Can P still be the P still be the subset of S? So that's it. All right. And since we have the binary search, let's write the binary search template first. Basically, we have the n is going to be length of removal, right? So the left equals to 0, right? R equals to n minus 1. Because in my case, this middle means that from index 0 to this index, to this middle index. So middle is included. That's why I use R is equal to n minus 1 here. And while as R is smaller than this one, right? Basically, middle is going to be the plus R minus L plus 1, this one, right? And then we have a if can remove, right? So basically, I'll call it helper function, or okay, so let's call it can remove. So we pass in the middle, right? Basically, this one checks if by removing 0 to middle index, if P is still in the subset of S, then we know, okay, L is going to be the middle, else R is going to be the middle minus 1, right? And since we're getting the maximum, right, the maximum will be L equal to middle. Otherwise, if we're getting the minimum, it will be R equals to middle in this case. But since we're getting the L, we're assigning the middle to L, we need to do a plus 1 here, right? So because this one, otherwise, if L is equal to 0 and R is equal to 1, right? So if we don't do plus 1 here, as you guys can see, the middle will be stuck at 0 forever, right? That's why we need to do a +1. So here we return the L +1 because we are returning we're returning how many K's we can remove, and this L and R it's 0 base, but K this is 1 based, right? That's why we're going to remove L +1. But there's one more thing we need to be careful here is because remember this template. So what this template telling us? It means that we're assuming there is an answer between the L and R, right? So which means that but there's but it could also be the answer is 0. 0 means that the we cannot remove anyone, right? Because as you guys can see, so even the L is equal to 0, we're still returning 1. Means that we're assuming by looking at this one, we're assuming there's always an answer right there. But between this 0 and n minus 1, I mean, for most of the binary search, that's the case. But for this one, at least the way I write it, it could also be a case that the binary search will not give us any result, which is the 0 case. So in this case, we can simply do one more check here. Basically, we return the L +1. Whenever this L is equal to R, we do one more check. So this one, right, and then else 0, right? That's the easy fix here. And then the only thing left is that can remove helper function, right? Can remove, it's going to be the middle. So this one is pretty straightforward, right? So it's like it's a very standard subset algorithm plus one more condition. Basically, I have a j is equal to 0. So this one is a pointer of p, right? And then since we need to remove something, so which means we're gonna remove set here, right? It's gonna be a set of removable, right, of this first middle index, right? So I'm doing this kind of set so that I can check the existence within O1 time. So and then the algorithm, so we loop through the first N1. Yeah, so this is going to be a length of S, right? N1 and then N2 is going to be a length of P, okay? So here we loop through we move the first pointer. So if I is not in the remove set, okay, and as I is equal to the pj, then we move the second pointer forward. And then if the j is equal to n2, we return true, right? Otherwise, return false in the end. So yeah, I think that's it. If I run the code, what? Oh, yeah. So this slice is already like a list. Okay, submit. Cool, so it passed, right? Because as you guys can see, so the time complexity for this one, the binary search, this one is log n, and can remove here, this is a O of n, right? So that's why it's a O as n log n solution here, and it will pass. Yeah, I think that's it, right? I mean, it's an interesting problem, but I see why people give it a lot of downvotes here, because I think a lot of people might have done the similar thing as I was trying to do, right? Basically, trying to find like a new algorithm that can solve this problem. With can check P if it's a subset of S with this removable within O of n time, but it turned out there's no such algorithm. That's why we had to go back to the very basic improvements, which is the binary search. Okay, right? Because the k the increasing of k will cause the can remove going down. That's why we can use binary search. Cool. I think that's it. Thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.